Before we get started on this problem, let's just quickly sketch out what we're dealing with. So we have a pivot point, then we have a board, and there's a rope at the end of the board, and there's a heavy piece of machinery that's set right here. Well, here's what's happening. The weight and the machinery is pushing down on the plank, okay? The rope is pulling upward on the plank. And the pivot point is pushing up on the plank too, but we're going to treat this as a torque problem. We'll take this as our pivot point. If that's the pivot point for all of our torques, we've really got two torques. There's the rope, which is tending to make the plank rotate this way. We have the weight of the machinery, which is tending to make the plank rotate this way. And if the plank's not going anywhere, these two torques have to be equal to each other. Now, if the machinery gets moved further and further out, this torque gets bigger and bigger and bigger. What that means is the force provided by the rope is going to have to get bigger and bigger and bigger. So at some point, the machinery is going to be as far out as it can be before snapping the rope, because the rope is going to have a certain maximum force that it can support, and that's related to its tensile strength. So that's what the problem's dealing with. And you can see we've got two pieces that we need to consider. First off, the tensile strength of the rope. We need to figure out how much force it can support. Then we have to solve a torque static problem right here. So let's go ahead and do some preparation for this problem. And there's two pieces that we have to prepare for. And the first piece we have to prepare for is thinking about the rope. Well, remember, tensile strength is defined this way. Okay, so if I have tensile strength, it's equal to the maximum force that something can support divided by its cross-section area. Now, we're interested in the maximum force the rope can support. The maximum force that the rope can support is therefore just equal to the tensile strength times the cross-section area. But the cross-section area of that, we'll assume it's a round piece of rope. It's just pi r squared. We're given its diameter, okay? And it's 7 millimeters in diameter. So the radius of the rope is 0.0035 meters. And we're told the tensile strength. We're told that the tensile strength is 6.0 times 10 to the 7th newtons per meter squared. So we have everything we need to be able to solve for the rope. Now for the next phase, let's think about the plank. Okay, now the plank situation looks like this. There's a little fulcrum right here. The plank goes like so. We're told that the plank is lightweight. By lightweight, let's assume that we mean massless. And so we don't have to worry about the center of gravity of the plank. We don't have to worry about the force due to that. But we've really got two forces. There's an upward tension force from the rope. There's a downward weight force on the plank due to the weight, or there's a downward force on the plank due to the weight of the machine. Okay, so I'm just going to say it's the weight of the machine because that's the magnitude of the force pushing down on the plank right here. We have these two. We also have a force from the support right here, a normal force right there. Now the plank's not going anywhere. So that implies it's in equilibrium. And if it's in equilibrium, the sum of the torques is equal to 0. Now, there's no torque due to the normal force at the pivot because I'm going to take my pivot point to be right here. It's a natural pivot, okay? So if we take our pivot point right here, there's no torque due to this force. There is a torque due to this one. There's a torque due to this one. We're asked to compute how far out from the pivot we can place the machinery. Well, we don't know. So we're going to go ahead and call that x. That's our unknown, which we're going to be looking for. The force of the rope is applied a distance of 3.5 meters out from the pivot because that's the length of the plank. So if the sum of the torques is equal to 0, we've got two torques. The torque of the rope is making the board rotate this way. The torque of the weight is making the board rotate this way. The magnitudes of these two torques have to be equal to each other if the net torque is going to be equal to 0. So that tells me this. This torque due to the weight is equal to the torque due to the tension, and we'll just consider magnitudes. Now both of the forces act at a right angle to the plank. So our sine phi factors in the torque equations both turn into 1. And so our torque equation just looks like this. The torque due to this force is equal to torque due to this one. The torque due to this one, magnitude is just W times X. The torque due to this force is just T times 3.5 meters. And so this is our basic relationship that we can use to solve for x. That's ultimately what we're going to be looking for here. Now, let's go ahead and complete our solution. What I'm going to do first is I'm going to look at the tensile strength of the rope, and I'm going to consider the maximum force that it can support. Well, we have an equation for this, and I'm just going to go ahead and put numbers in. The maximum force that the rope can support is 6.0 times 10 to the 7th newtons per meter squared, and that's times pi r squared. Well, r is the radius of the rope. That's 0.0035 meters. And that's squared, and I can compute the maximum force. You can see I'm going to get meters squared. That cancels with meters squared. I'm left with newtons. That's a good check on our work. If I put numbers in and I calculate it, I get the maximum force that the rope can support is 2,310 newtons. Now, this is a two significant figure problem, but I'm keeping one extra significant figure because this is an intermediate stage of the calculation. Now, next up, we're going to consider the greatest distance that the center of gravity of the machine can be without snapping the rope. Well, we're going to use this relationship for that. Our basic relationship for the static equilibrium of the board is this: the weight force times the distance that the machine is from the pivot. And by the machine, I mean the center of gravity of the machine is just equal to the tension in the rope times 3.5 meters. But we want to put the machine as far out as we can. Now, as x gets bigger, what happens is t gets bigger. Well, we know the biggest value that the tension force can have is 2,310 newtons. Okay, we know that that's true. We also can calculate what the weight force is. Okay, the weight force, the weight of the machine, is just m times g. M times g is 800 kilograms. It's an 800 kilogram piece of machinery times 9.8 meters per second squared. That's equal to 7,840 newtons, okay? Now I want to notice something here. The weight of the machine is greater than the tension force of the rope, or the greatest than the maximum tension force that the rope can support. And so clearly, as you move this machine further and further out, at some point this rope is going to snap, because if the machine was all the way here at the end, basically all of its weight would be supported by the rope, and the rope can't support as much force as the weight of the machine. So it's going to break. Now notice this. This number right here is about a third of this number right here. So I'm guessing that the distance right here out from the pivot point is going to be about a third of the length of the board. That's what I'm going to guess. But here's what I'm going to do. I'm just going to rewrite this expression. We're trying to solve for the distance. How far out can the machinery be from the pivot point? Well, the distance is x. If I rewrite this expression to solve for x, it's this. It's t over w times 3.5 meters. Well, t is the maximum force the rope can support. That's 2,310 newtons. The weight of the machinery is 7,840 newtons. Multiply that by 3.5 meters, and I get to two significant figures, 1.0 meters. That's my answer to part B. Now, the answer to part A is what is the maximum force the rope can support. We calculated that up here to be 2,310 newtons. But if we're going to report this, we want to round it to two significant figures because it's a two significant figure problem. So we round this to 2,300 newtons for reporting our result. That's the answer to part A. Now let's do an assessment. We said when we looked at the magnitude of these two forces that we expected the machine to be able to be about a third of the way out from the pivot point. And in fact, we got 1.0 meters. That's about a third of 3.5 meters. And so our assessment is that our solution to the problem matches our understanding of the way the world works.